Okay, so I think we can start it now.
Yes, sir.
You already finished part A with Dr. Shahnas sir. Okay, so I will take part B. It will start from the column. So I'll start with lecture 5. It's a column. And column and beam. Most of the time you will see people use these two terms together because most of the structure, when you design, when you analyze, either fall in column criteria or might be on a beam criteria. Okay, either you have to think this is a beam or you have to think this is a column. So you need to identify the difference between the beam and column. Normally, you might think a vertical member is always column, like we use in the building. But actually, definition is a little bit different of column. Column, it might be a horizontal or it might be a vertical member. But it has some difference from the beam. Number one thing, that it will always take compressive load. In say a vertical member, support at the bottom, so reaction force will work upward. So these two members is, although is a one is horizontal, other one is vertical, but you see they have certain criteria. Both are taking compressive load, and direction of load is parallel to the longitudinal axis of the body. This is the difference. But in beam, say this is beam, and if you have a support, say fixed support in the left side, then you can apply load anywhere, right? What you see, the direction of the load, it make angle 90 degree with the longitudinal axis of the body. So this is the axis of the body and it make 90 degree angle. So this will be beam because the load is applied perpendicular to the longitudinal axis of the body. And this type of load also is called transverse load. Transverse load. But in column, load always apply along longitudinal axis of the beam or parallel to the longitudinal axis of the beam and has to be always compressive. Now, if you have a, say, a rectangular body, you can apply load at the center of the cross section, right over here, or you can apply load at the corner, but still load will be parallel to the longitudinal axis of the body. See, I'm showing a blue color, I'm sorry, yellow color pencil box, right? This pencil box I am holding on my hand and applying load at the top. And you see I apply load at the center of cross section. So this compressive load is going along longitudinal axis of the body, right? But I can apply over here at the corner. But still, direction of load is parallel to the longitudinal axis of the body. So this load, instead of applying at the center, if we apply at the corner, that is called eccentric load. Okay. So let's see what is the definition of the column. It's a member or parts which is subject to axial compressive load. This is one definition, that it always take axial compressive load such that direction of load may be coincided or parallel to the centroidal axis or eccentric from the centroidal axis. This is the definition of the column. It doesn't matter, it is vertical or it is horizontal. You have to match with this criteria. The load has to be compressive and load is parallel to the longitudinal axis of the body, or centroidal axis of the body. Now, where is column used? Used in the aircraft, in the ship. You see a lot of bridge. They use the truss that is also compressive. Then building structure. You will see a lot of building nowadays making with the I-beam. The load is, like compressive load, and all the column used in the building. Instead of concrete, most nowadays you see in the neighborhood they're using I-beam for a vertical column. Okay. And how column fail? It's a column is failed by buckle. That means lateral deflection of the column. Lateral deflection means, say you have a column and you apply load at the top. So in bottom, if you have a support, then support will react upward. So this is compressive load, right? So then after you apply load, it gradually, let me pick up it will bend like that. That bending is called lateral deflection of the column. Okay. Now, type of column. There are, depending on the not in terms of length, depending on the geometry of the cross section and the length. Based on these two criteria, column is defined in 4 types. Number 1 is called long column with central loading. Central load means direction of the load going through the CG of the cross section. So that is called central loading. Then intermediate length column with central loading. Intermediate means is not long, is not short, right? Other one is a column with eccentric loading. Short or strut with eccentric loading. So you see, they are calling some column long, short, and intermediate, and so calling strut with eccentric loading. Eccentric loading, we already explained a little bit that, say, a column has circular cross section. So if I draw the cross section, it will like that, right? So if you apply the load at the center, right over here, that means load going through the CG of the cross section. So this will be not eccentric. That means central loading. Load are going through the centroidal axis or longitudinal axis of the body. But instead of over here, you will apply load over here. So how much far offset from the CG? This much, right? So this distance from here to here is called eccentricity. So if you apply CG right over here, but if you apply load over here, in that case it is called eccentric loading. Okay. So you got some concept that what is eccentric loading. Now, there is a one term used in the column is called critical load of the column. In the beam, we use formula, right? Sigma equal to my by I or mc by I, right? So, but in the column, similarly, we need to have a formula. Formula for what? To figure out the critical load or critical stress. If you are able to figure out a critical load, that means how much maximum load a column can take. So that load, if I say load equal to PR, load equal to PR, what will be the stress? Sigma critical. Sigma critical will be PR divided by area, right? Then you can say PR by area. This is critical stress. So you need to figure out that how much maximum load a column can carry. Then you can figure out the what will be the stress in the column by divided by that area. Okay. Now, you know that you need to figure out the critical load. Now, what does it mean physically? Or actually what you are meaning, or I am meaning about critical load of the column. For example, if you apply, say you have a column like that, vertical member, and you apply some load from the top, and it will react to the bottom, right? Say, for example, initially you apply load 100 Newton, column is deflected a little bit, but still remains straight. You apply 200 Newton, you apply gradually increasing a load, 300, say 350 Newton. So you apply 100 Newton, this column is buckled a little bit like that. My line is not perfectly shaped. Let's see, I can draw it. Say, just bend a little bit. 200 Newton, still it bend a little bit, but more than previous one, right? Because you increase the load. 350 pound increase, it bend more, but still it is carry the load. But you increase little bit more, 350 to 355. When you apply 355 Newton, the column is breakdown. So this 350 is the critical load of the column, because it remains a little bit deflected shape, but still it able to carry the load. So what is the definition of critical load? We say critical load of a cylinder column. Cylinder means slim. And how we consider a body slim? Or normally we call Bangla shuru. What does it mean? That means you need to compare with height and cross section. Sometimes you see a human body is very tall, he might be more weight than you, but due to the he is very tall, he look like slim body, right? But sometimes you'll see a shorter body, weight is not that much, but still look like he has more weight, right? So what I'm saying, a column is slim or slender. It is depend on the cross section of the column and also length of the column. Say a column is very huge cross section, but its length is very high. Say a column has a cross section this type, but is higher length. So this might be a slim column. Again, a column is very slim cross section, but it is short, length is short. Then this might be behave like a short column. And though this cross section is high, but is working like a slim column. Okay. So a column is short, long, slim. It depends on some geometry. That is cross section of the column and also length of the column. So critical load of the column, that means it is a magnitude of axial force just enough or sufficient to keep the column or bar slightly deflected configuration. And right over here you see a pin in a bar, both end is pin and is buckled a little bit due to the load PR. And this PR is called P critical. For example, this PR equal to, say, found by calculate. After calculation, you got PR 5,000 Newton. That means this is the maximum amount of load you can apply in that column. It will not fail, but it will buckle a little bit. Say it will buckle. So this 5,000 Newton is the P critical. Why? If you increase a little bit from 5,000 to, I'm saying 5,050 Newton, or 25 or 5 Newton, After increase immediately, then column you'll see break. I'll break it over here. Anywhere it will break, right? It will break at the middle because at the middle it has a maximum stress. So this 5,000 load, we'll call it critical load of the column. So you need to know the definition. Now, to figure out the stress in a beam, you need to know what is the beam, what is the end support, what is the moment of inertia, what is the bending stress, what is the shear stress of the beam. So similarly, if you are studying column, so you need to derive a formula that how we can figure out the critical load of the column. To derive that formula, you need to know some basic term, some basic geometry of the column. Number one, you need to know what is the length of the column. Length means physical length. Okay. Then you need to know a radius of gyration of the column. Radius of gyration you already know from your engineering mechanics. So radius of gyration normally it is expressed by letter K or rho. Some book they use rho and some book they use K. So K or rho equal to I minimum by A. That will be the radius of gyration. And slenderness ratio is L by K or L by rho is called slenderness ratio. What does it mean slender? Slender kind of meaning kind of slim. A body is slim. Say body is slim that depend on value of radius of gyration. You see, this L by K is higher, mean column is slim, or we can call column is long. How? You see, K value is low, then you will get the slenderness ratio is high, right? So when K value will be low, K value will be low if you increase the A cross section, right? Cross section is increased or cross section is decreased, then K value will be high, right? If K value is high, then L by K will be low. If K value is decreased, then L by K will be high. So that's you remember that I need to know what is length of the column, what is radius gyration, and what is the slenderness ratio. And other thing, that critical load of the column, it depends on the end condition of the column. End condition mean both end in the column might be in a pin support, or both end might be in fixed support. So for example, if you look over here in the column and if you apply compressive load, then it is deflected. Now if you look to the end condition, this end is a pin, this end is a pin. So after we apply load, it is deflected. Okay. Now same length of column. Now in the bottom, instead of deflected pin, this is a fixed support. And right over here, also fixed support. You see. The roller is at the not at the column in the support. So if we apply load, this due to this roller, it can go down or go up. So but end of the column is both end is fixed. So a column carry higher load or lower load depends on the end condition. Similarly, in the right side, you see this end is fixed, but this end is free. So obviously this will carry less load. Okay. For example, if you say you are traveling somewhere, you get down from the rail station or from the bus, but nobody is there to help you, and you have a bag with 50 kg bag. What will you do? You will walk and take it in your head, for example. So as a human body, your body will work like a column. Now, say you don't have no shoe. You get down in the Newark airport and road is icy. Any reason emergency situation, you see nothing is there. Nobody there, your friend supposed to come in the airport, but no. Now you are walking with a 25 kg suitcase on your head and you are bare feet. What happened? Most probably you will not able to carry, you most chance that you will might be fall down, right? But if you have a boot, a nice shoe in your feet, then you will have more uh, fix into the ground, right? Uh, what is called that one? That means you have more friction with the ground, less possibility that you will slip. Then instead of 15 kg, in that situation, you might be able to carry 20 kg. Okay, so that is the example of how end condition is vary. Now, what is the pin support mean? Pin support means, say, I am holding a pen with my finger right over here. What does it mean? Pin support mean if this is X, this pen cannot move along X axis, cannot move along Y axis, but it can rotate. So this is the example of pin support. Now, if this is fixed, if I say holding like that, what does it mean? That means it cannot move along X axis, it cannot move along Y axis, also it cannot rotate. That is called fixed support. So if column end is fixed, obviously it carries more load, and column end is spin, it will carry less load than the fixed end column. Okay. So just remember that depends on end condition, column load vary. Now, what is our target? We need to figure out the formula. How we can figure out the formula? You see, column and the beam, they work almost little bit same way. Say you have a beam, say you have a reaction at the both sides. Right here you apply load. Then due to the column will beam will deflect like that, right? So what does it mean? That means it's deflected like a curve. So how look like a curve? This one, right? So similarly, and this one, this curve, I can say it is a part of a circle, because if I extend this line, then this will be actually a circle. So if it is a circle, then definitely it will have a radius. So that radius I'm calling it rho. Okay. Similarly, you see right over here, this is graph, right? I'm saying this curve, not straight line. So what is the difference between graph and straight line? In a straight line, you will have constant slope, but in a curve, slope is vary every point, and slope also vary with the radius at this point. Right over here, you have one radius, right over here, one, right over here, one radius. So if radius increase, what does it mean? What is the radius of a straight line? Say you have a circle, small circle, you have radius R1. To increase the radius, circle will be more bigger. We increase more, circle will be more bigger. You increase more, bigger. If make radius infinite, then what will be this line? You see, gradually they are less bending. So if make the radius infinity, that means this line will be straight line. So if rho increase, then it means that you have less deflection, and rho decrease, it has high deflection. So, and also when a curve become like that, what is the reason? And straight line going like that. The straight line slope is constant, but in a curve, every point slope is changing its magnitude respect to this radius. Now, mathematically, we can found a relationship between radius of curvature is 1 by rho. Rho is the radius of curvature. Then 1 by rho equal to this value. This is a formula taken from mathematics. Now, right over here, I miss one term. This will be 3 by 2 outside of bracket. Okay. And this 1 by rho, you see it has some relation with slope. D square y by dx square, dy by dx whole square. Now, this dy by dx, this higher order term, if we expand, you will get dy by dx whole cube, first term, 1 plus this term. So if you neglect higher order term, then 1 by rho equal to, you will get this one. Okay. Now, why a beam or a column bend? What is the reason? And sometimes you see it is bending at the middle or at one side maximum. Right over here is bending maximum. Why? What is the reason? Anyone? Hello? Do you know anyone why?
No.
Why your beam bending maximum right over here? What is the reason? No? Okay, Mr. Ronnie. Okay, because why beam is bend like that? At the end, it has less bending. At the middle, it has high bending. And right over here is low bending. Deflection is low. What is the reason? Because it's subject to bending moment. Everywhere it has a subject to bending. And due to the bending, it bent. So this bending moment is very high, then the radius will be sense. So this bending moment and radius of curvature has some relationship. So we will see over here two relationships. Number one, 1 by radius of curvature equal to this mass. Again, relationship between the radius of curvature and bending moment and modulus of elasticity is m equal to ei by rho. Now, from these two equations, we can get something. What we can get? If you substitute 1 by rho right over here, then we can get d square x by dy square equal to some function of m. So then you'll get a differential equation, second order differential equation. And by solving that differential equation, we can derive the formula for column. So let's see how we can use that formula. You see, say a column is subject to, or it might be beam, compressive load. It has compressive load right over here. And after we apply load, it deflects a little bit. So why is the M coming? If we apply axial load, but over here M comes, because at every point it creates bending moment in the column. For beam, same thing. For beam, what happens? Say you have a cantilever beam. Your beam support, for example, left side. If we apply load right over here, then it is bend like that. Why? Because every point bending moment is working. Now we have this, that's why we bring bending moment. M equal to ei by 1 by rho. Then we don't know 1 by rho equal to this mass, right? Now these two equations, if you put 1 by rho value right over here and simplify, you'll get this equation. And this equation is called Euler-Bernoulli equation. This is very important equation. You can use it to figure out the beam deflection. Okay, and also we can use this equation to solve the equation of a column. Okay, so let's see how we can use this equation. Right over here, you see, just showing you a aircraft structure. And you will see here a lot of structure. You cannot see from outside because there is a skin in the outer panel, so you cannot see. You see there is some round shape structure right over here. And right over here, you see it's passing left side to right side, this kind of floor beam. Okay. And you see, could you hold down just 1 second? Okay. Okay. Are you able to hear me? Hello?
Yes, sir.
Hello?
Yes, sir.
Yes,
Okay.
sir.
So in the figure, you see some structure right over here, right? This one, going left to right. Okay. This one kind of beam. Then you see this is a frame, round shape frame. And so lot of structure you will see it work like a column. For example, in the tail, you see some member is going at certain angle, going upward, right? So all of the weight of the rear wing is applying compressive load in those structures. So they carry some compressive load. That means they work like a column. Similarly, if you look in other picture, right over here, I don't see clear picture over here. I show you over here. Okay. This one is picture of real aircraft photograph. So you see right over here, this is a floor beam. And they have every 20 inch or 24 inch. The one frame of beam over here going left side to right side. They might have one more over here, one more over here, from front to tail. Okay. Then over the floor beam, they have a floor panel. So if you walk down over the panel, or you carry some load or cargo load, actually the load is going to the beam. Then what will happen? This beam is horizontal, right? Beam is horizontal going left to right. Both this side attached to this round shaped frame, the left side and right side. So if you put something top of the floor beam, then this floor beam will deflect. So it will deflect a little bit, right? How much it will deflect? Deflection? You study beam deflection, right? Depends on the type of load, type of geometry of the beam. But I don't want to deflect that beam. I like to minimize the deflection. You know what we will do? You attach some structure with the bottom floor. So these two members will carry the compressive load. They work like a column. Similarly, right over here, you see this one. This one is working like column. Similarly, you see a beam right over here in the lower cargo bay. Right over here, right over here. So if I attach something between the top floor beam to lower cargo beam, then I draw the red color. Those members work like a column. Similarly, right over here. This is column, this is also column. Though it's saying stanchion, that means vertical member carrying compressive load. And you see those structure right over here is going all the way left side to a front side to tail section. That is called stringer, like this one. Okay. And those stringer cross section sometimes is called head cross section, like your cap. So cross section might be like that. And sometimes those cross section might be C channel, like C, letter C, like that. Okay. So depends on the load carrying capacity. They also might be work like a compressive member. Okay, like this one, C channel. This one, this one, this was also a column. So similarly, they have column in even you travel in boat. If you see empty boat, you will see floor beam, right? It's travel from, say, if I draw a case of a boat, just just a case, and you see just 6 or 12 inch from the top, they have some vertical member going left side to right side, right? And they put something top of this beam and you walk or you sit down. But your beam or your boat is too wide. Then you put something to deflect. So what will you do? In the lower side, if I make the cross section, that means this is your boat. This is your floor beam of your boat. Then you attach some structure to reduce the deflection. That means when you sit over here, then this load ultimately going through this member. That means they work like a column. Okay. And here is a one more example, like one more case. You see this is the older aircraft. You see right over here, this structure, those structure is carrying weight of the upper wing. What does it mean? That means compressive load they're carrying. Similarly, structure this one, also those kind of little bit kind type of rectangular type body. So they are carrying compressive load. So landing gear of aircraft carry compressive load. Okay. And you see all the big ship carrying all the goods, container, they under the floor beam, most of the structure, they're carrying compressive load. So a lot of application of columns. I just put some formula over here. We might need it later on. So we'll not discuss it that one. Now, how we can figure out the compressive load or critical load of a column? How we can figure out? You see that we are considering a long column, long and slim column. Now, a long and slim, how you will say column is slim or column is long? It depends on some criteria. Number one thing depends on its physical length, depends on its cross section, and also depends on its end condition. So we'll figure out later on that how you can measure or how you can identify that a column is long and another column is short. How you can figure out? You have two options. You can measure with the tape, right? Even you measure with the tape, say a column is 200 feet long. So you'll say this is a long column. But its cross section is too high, it might don't behave like a long column. It might work like a short column. Similarly, a very small column, cross section is very narrow or very low, though it is a short, but it might not behave like a short column. For example, if you buy a steel scale, say 12 inch long, right? You apply load like that, what happens? It will ultimately buckle because cross section is so thin that it cannot take compressive load, buckle immediately. So it behave like a short column. And what is the moment of inertia? Anyone? Anyone? Moment of inertia mean if you have high moment of inertia, that means it will offer more resistance to buckle. If you have low moment of inertia, then it will buckle easily. So if you increase the moment of inertia, it will offer more resistance. That means it will not want to buckle. That's why you see that moment of radius of gyration and slenderness ratio, if you look to the definition over here, that radius of gyration equal to I minimum by A. What is the reason? Because a column will buckle in respect to where moment of inertia is less. For example, if I draw a cross section of your steel scale, the cross section like that, right? Very narrow. And how it is long. This is your steel scale. Say it is this type of long, right? This is long. This is long. Now you can apply load from the top. Then what will happen? It automatically buckle along this direction, right? If I take a car, it buckle this direction. But other direction, this direction, it buckle like that. How I can give you example? Say right now my hand is a comb, your pocket comb, right? So if I apply compressive load, what happens? You see, it buckle along this direction, right? But is it able to buckle along opposite direction, this direction? I cannot do it because it offers higher resistance to buckle due to the moment of inertia. So if this length, I'm saying this is B and this is H. Along this direction is I'm saying X, top direction I'm saying Y. So if I make IXX, then what will be value? 1 by 12 BH cube. And what will be IYY? Then IYY, it will be 1 by 12 HB cube. See, which one is higher? You see, IY is higher because H into B cube, B is higher. And IXX 1 by 12 BH cube. So this value is lower than IYY. That's why I'm showing you that a comb, you just apply load, it bend along this direction, but it is not bending along this direction because this direction, it has IX direction, it has less moment of inertia. So that's why radius of gyration, you have to use I minimum square root of I minimum by A. Now, go back to our derivation. So we are thinking a long slender bar of length L and cross-sectional area is A. Area is A, is subject to under axial compressive load P, and bar is remain deflected shape between two pin support, between this pin support and this support, as shown in figure. Now, why this bar is bending right over here more at the two end is less? Because in every section, and there is some bending on, due to the bending moment, it is bending. But you are not able to see because the internal load. But we can figure out that how much bending actually working in the cross section of the column. Okay, so our assumption, everything you derive, we need to make some assumption. Number one assumption, in most cases, we work with only isotropic material and homogeneous material. We say material is isotropic and homogeneous. But even we derive the formula, the material is homogeneous and isotropic. Nothing is 100% isotropic, 100% homogeneous. No. Nothing 100% pure in the world. So material of a Hooke's law. This is one assumption. Then cross section of the bar remain constant throughout the length. Even a pen, you see diameter is constant, right? That will be assumed. But reality, what will happen? It might be not constant. There might be same something. But when you derive the formula, we are assuming the cross section of the column is uniform or same throughout the length. So that's why we are making some assumption, but those assumptions might be 100% not right. Because you buy material from a company and they are telling you, okay, this is the homogeneous material, isotropic. There is a 5 ingredient alloy, but they're mixing uniformly. But might be not true. Might be one side you have higher ingredient, one ingredient, and same ingredient in other side might be has less concentration. So anything you make, then you do the test and make sure your test result match with your analysis. Then you can say, okay, my analytical solution or whatever formula you derive, that is good. Okay, so that's why for simplification, we have to use this formula. If you don't say material is homogeneous or isotropic, then you have to consider material anisotropic. That means you cannot use the single modulus of elasticity. You have to use EX, EY. That means modulus of elasticity is different along all 3 axes. Okay. Any questions so far? Hello? Anyone? Hello? Are you there?
Yes, sir.
Okay. Any question?
No, sir.
No? How long our class?
Sir, class time is over.
Class time is over. But
Yes, sir.
all of you remain silent. How much over?
Sir, it's
Sir.
already past 3:30.
3:30.
Yes, sir.
Okay. How much minutes I passed?
Only 2 or 3 minutes.
2 or 3 minutes.
3 minutes.
2, 3 minutes. Okay. Hold on 1 second. Okay, from next class, in last 5 minutes, I'll request you to unmute all the 5 or unmute all of you, and I might ask some question. I'll call Mr. Rafat Alam, roll 23. Then I'll ask some question. Okay, and depending on that answer, you might get some mark. And if you stay quiet, you'll not get any mark. Okay, because we don't get any response from you. Okay, better to have some response, and you should ask some question that, and you should not feel shy. I already told you about the fluid mechanics, because if you feel shy, then I'm not able to answer your question. Anyway, we're supposed to have a fluid class with you today, right? Hello? Hello?